Hi, I'm Gaston Fermandois from Santa Maria University in Santiago de Chile. The title of this talk is Adaptive Model-Based Compensation with Robust Tuning for Real-Time Hardware Simulation. Let's begin. Real-time hardware simulation is an experimental method for dynamics testing that was established in 1992. A structure is divided in two components, a critical element that is tested in the laboratory and the rest of the structure which is simulated numerically. The interaction between these two substructures is enforced through the use of actuators and sensors. The challenge is to synchronize these two substructures in real time. To do that, we usually consider the design of dynamic compensators in order to synchronize both signals. But the problem is that these compensators are usually designed considering the incorporation of the specimen. To do that, we need to conduct a system identification of the control plan, which is first of all very cumbersome, and second of all can introduce premature damage to the specimen. So the question is it possible to design one dynamic compensator for a set of uncertain substructures with guaranteed robustness? The objectives of this study are as follows. Design an adaptive compensator without prior knowledge of the structural properties of physical specimens, and have a rationale method to define the adaptive parameter gains, and finally design controller which is not required, that does not require modeling of the physical specimen to avoid premature damage. In this study, we propose robust calibration for adaptive model-based compensation. The idea is the following. We start with a given value of the adaptive gains gamma, and we conduct offline simulations of virtual plans that does not have information whatsoever of the specimen interaction. We include different target displacements and randomness on the virtual control plans in order to collect the performance index J2 for each random simulation. This performance index J2 is basically the normalized root mean square error between the measured signal and the target signal. Then we calculate something that we call the robustness indicator, which in this case is the mean value of the J2s for all the random simulations. And we feed that information into an optimizer in order to minimize the R2 index, and we collect the optimal value of gamma star that will create this situation. For numerical validation, we consider the virtual real-time hardware simulation problem that was proposed by Silva et al. In 2019. The figure on the left shows basically this is a three-story building with a single degree of freedom experimental substructure that is considered for the purpose of the study. We consider a servo-hydraulic actuator model, including specimen interaction and parameter uncertainty in both the experimental substructure and the values of the actuator. Additional cases on this study are that we consider higher uncertainty and nonlinear specimen compared to the original benchmark. Regarding the adaptive gains calibration, the objective is to find the value of gamma star, which minimizes the objective function R2. We visualize the design space in this figure, where we can see values from gamma 0 to gamma 3, where the red crosses are the optimal gains that were obtained through particle swarm optimization. The yellow region is the infeasible region, where we will have always instability of our virtual RTHS, and this basically considers values of gamma that are too high, that will create instability no matter what. The cyan regions are basically situations where we have slow adaptation, but is stable, but still it's not an optimal performance for this kind of study, for this kind of test. And the blue regions are basically suboptimal values that can be chosen to improve robustness if we have these values to be as far away from the invisible space as possible. The results for case 1 from virtual RTHS benchmark is shown in this slide. This is the nominal experimental substructure subjected to El Centro scale 60% earthquake. And we can see from this figure that the synchronization between the target displacement and the measurement displacement is quite good, with errors that are not greater than 1.7% in the J2 performance indicator. Regarding the adaptation, the black curves here show how the A parameters from A0 to A3 adapt in time. And this is without any information whatsoever of the specimen interaction at the beginning of the test. And we can see that the parameters will adapt fast at the beginning of the stroke motion and will converge to the identified values of the control plan with specimen interaction, which is something that is desired. Regarding the results in frequency domain, we can see that the initial model that does not consider any specimen interaction, which is this red curve over here, after the adaptation will yield results that are basically the same for the plant that has been identified up to the region of 30 Hertz, which is the cutoff frequency of the low-pass filter we consider in the framework. Results with different partitionings, earthquakes, and other experimental substructures show that the framework has excellent tracking results with a performance index J2 with values that are less than 3%, which is quite reasonable considering the uncertainty that we included in this task. So to conclude, the adaptive control improves the model-based compensation. The initial compensator is designed independent from actual actuator specimen interaction. The adaptive gains are calibrated to achieve robustness and performance. Excellent results in virtual real-time hybrid simulation with uncertain linear and nonlinear system is shown. And for future work, we would like to validate this framework through experimental tests. And we're looking forward to implement this framework for multi-axial RTHS. With that, I would like to thank you for your attention. And if you have any questions, you can reach me by email or through my Twitter account. And you're also invited to visit our webpage. Thanks.